We're going deep today, deep into the earth, actually, to unearth the science behind getting valuable stuff out of the ground.
Yeah, it's a whole hidden world down there.
It really is. And today we're tackling heap leaching. You know, that process where you basically make a mountain of crushed rock and pour chemicals over it to dissolve out the good stuff like copper or gold.
Exactly. It's a surprisingly elegant technique when you think about it. You're using clever chemistry to extract valuable metals from ore that's otherwise too low grade to be worth processing by traditional methods.
So it's not exactly alchemy, but there's definitely a magic to it.
Right?
We've got a stack of research papers here that delve into all the fascinating details. We'll be exploring how to model these leaching processes, the crucial role of drainage systems.
And we'll also be digging into some exciting new developments in green gold extraction.
Oh yeah, that's a hot topic.
It is. And we'll also be examining the environmental legacy of past mining operations.
Like that study on residual contamination at a former uranium site.
Exactly. We'll even touch on how fluids move through these massive heaps, how different factors affect copper and zinc extraction.
And some pretty mind-bending thermodynamic theories, too.
It's going to be a wild ride.
Buckle up. This deep dive is all about giving you a clear understanding of the key aspects of heap leaching.
All right, let's get started.
Okay, so first things first. How do we even begin to describe what's going on inside these massive heaps?
Well, one of the papers dives into this really cool concept of building analytical models. It's all about trying to represent these incredibly complex processes with relatively straightforward equations.
Equations, as in math. I'm already lost.
It sounds intimidating, but stick with me. It's actually pretty intuitive. Think of these models as a way to understand and even predict how much metal you can get out of a heap over a certain time period.
Okay, so instead of just crossing our fingers and hoping for the best.
Right, these models give you a more scientific approach.
And I see that these aren't just random formulas pulled out of thin air. They're based on solid principles like the Bernoulli equation, which governs fluid flow.
Exactly. And they also use what are called constitutive equations, which basically describe how the materials involved, like the ore particles, behave under different conditions. And the really neat thing is that these models consider different scales, from tiny particles to the entire heap. It's like zooming in and out to get the full picture.
Multi-scale modeling, that's so hot right now.
It is. And the paper even talks about a family of models based on a parameter they call ENT.
INT, is that
Yeah.
like a scientific ranking?
Kind of. Think of it like a tunable knob on the model. By changing the value of ENT, you can adjust the model to account for different leaching behaviors. It can even have fractional values, which adds a layer of sophistication.
Fractional values like 1.5 or 2.7. So we're not just dealing with whole numbers here.
You got it. And the paper introduces these key equations, equation 2 and equation 3. Don't worry, we won't go into the nitty-gritty math here, but they basically let you calculate how much metal you're going to recover. That's RT over time T. These equations also include factors like RL, which is the maximum possible recovery, K, which is a rate constant, and UV, which is a delay factor.
Wait, a delay factor. Like there's a lag before the leaching really gets going.
Exactly. It's not like you flip a switch and boom, all the metal comes pouring out. There's a bit of a ramp-up period.
That makes sense. And I see here that when ENT equals 1, the equation simplifies into what they call a first-order kinetics model. Is that a common one?
It's a classic. And get this, they compared this first-order model to actual experimental data from heaps of different heights, and it did a pretty good job of predicting what was going on.
So even a relatively simple model can be surprisingly accurate. But they didn't just start at the first-order model, did they?
Nope. They got ambitious and decided to compare their model to results from another well-established model developed by Dixon and Hendricks. And they were able to replicate those results, even with different particle sizes and what's called superficial velocities.
Superficial velocities. That sounds fancy. What is that exactly?
Basically, it's the overall speed at which the leaching solution is flowing through the heap. It's like a gentle rain shower passing through a porous material.
Okay, that makes sense. So they're basically testing their model under a variety of conditions. And I see that they even use their model to estimate outcomes for conditions that weren't directly tested by Dixon and Hendricks. That's pretty cool.
It is. It shows that their model has predictive power. And they also introduced variations on their model with different values of N, which can be tailored to specific situations and even simplified to focus on the most important factors.
Like a head of tools for different leaching jobs.
Precisely.
Now, the paper also mentioned that Peterson and Dixon proposed modeling bioleaching at multiple scales, looking at things at the particle level, then clusters of particles, and finally the entire heap. That sounds super detailed.
It's a way to get a really granular understanding of what's happening.
And to see how well their model matched the real-world data, they used statistical measures like the sum of squared errors, or SSE,
Right.
and a deviation function. Right.
They even used advanced computer techniques like GAMS-MINOS to refine their model and find the best fit to the data.
So there's a lot of heavy-duty math behind the scenes.
Definitely. And they also explored how things like particle size and superficial velocity affect the overall recovery, even using simulated data from the Dixon and Hendricks model to fill in some gaps where they didn't have real-world data.
It's like using one model to power up another model, modelception.
You got it.
So it's clear that these models, while simplified representations of reality, can be super useful for understanding, predicting, and optimizing heap leaching. But let's move from the theoretical to the practical. We've got a paper here that's all about drainage systems.
Ah, yes, the often overlooked but absolutely vital drainage system.
It's like the plumbing of the heap leaching world.
Exactly. Without a good drainage system, everything grinds to a halt. This paper actually proposes specific equations for calculating things like the thickness of the gravelly drainage layer at the bottom of the heap and the diameter of the pipes used to carry the leachate away.
So these equations help engineers design the drainage system.
Yes, they give engineers the tools to determine the right size for the pipes and the thickness of the gravel layer, taking into account things like how much liquid is flowing through the system, how permeable the materials are.
Safety margins.
Yeah.
And even the potential for blockages, right? I mean, those pipes have to handle a lot of nasty stuff.
You got it. And the paper emphasizes that while these equations can be used individually in simple cases, in reality, a drainage system is a complex network. You got to look at how all the pieces fit together.
It's like a giant interconnected puzzle.
Exactly. And they actually apply these equations to real-world heap leaching operations, to Rome and Sarcheshme too. They even highlight specific design challenges, like the steep slopes at the Sarcheshme 2 site, which make installing those drainage pipes tricky.
So no one-size-fits-all solution here.
Definitely not. For Sarcheshme 2, they proposed a clever redesign. Instead of having a uniform gravel layer, they varied the thickness based on those equations, putting the main pipes in the valley floors. They even calculated specific pipe diameters for different sections of the heap. It's all about tailoring the drainage system to the unique features of the site.
Talk about attention to detail. They even mentioned something called a replacement factor, which, from what I gather, is a measure of how effectively the drainage system removes the leachate.
Right. It considers the overall geometry of the heap.
And they wrapped up with specific recommendations for those two sites. For Tarim, they suggested a parallel arrangement of pipes with a constant gravel thickness. But for Sarcheshme 2, with those sloping valley floors, they went with parallel pipes and a gravel layer that gradually gets thicker towards the center of the heap.
So it's all about working with the terrain.
It's amazing how much thought goes into something as seemingly simple as drainage. But it's clearly a crucial piece of the puzzle. Now, let's switch gears and talk about the environmental impact. One of our papers asks a really provocative question. Is there a green chemistry approach for leaching gold?
This is a huge area of research right now. The idea of green gold and sustainable mining is gaining momentum. Everyone wants to minimize the environmental footprint of gold extraction, especially since traditional methods rely on cyanide, which is,
Not exactly eco-friendly.
yeah, highly toxic is an understatement. So this paper delves into the principles of green chemistry, things like preventing pollution in the first place.
Atom economy, which is about using your starting materials as efficiently as possible.
Exactly. And, of course, using safer chemicals and having real-time monitoring to catch any potential problems early on. They then compare different leaching reagents for gold cyanide, thiocyanate, thiosulfate, and thiourea using these green chemistry principles as a benchmark.
So they're looking at alternatives to cyanide.
Yes. But the author also points out that defining and measuring sustainability in mining is a bit of a slippery slope. It's a complex concept with many facets.
It's not just about swapping one chemical for another, it's about a whole system-level approach. But I see the paper also highlights how the industry is responding to this call for greater sustainability. They mention the Mining, Minerals, and Sustainable Development Project, or MMSD.
Yes, the MMSD report emphasizes integrating economic activity with environmental responsibility, social well-being, and good governance.
So it's not just about profits, it's about the triple bottom line: people, planet, and profit.
Yeah.
And the paper connects these broad principles back to the specifics of using chemicals in metallurgical processing.
Prevention, atom economy, safer auxiliaries, and real-time analysis are all key. The paper also brings up the issue of mining waste, which is enormous, and the importance of planning for mine closure right from the get-go.
So thinking about the end of the mine's life before you even start digging.
Exactly. We can't just leave a mess for future generations to clean up. The paper really emphasizes the need for robust environmental management systems that assess the full impact of mining operations and work to preserve biodiversity. It's all about a life cycle approach to mining.
It's clear that the industry is taking this seriously. And shifting from future practices to past legacies, we've got a paper here that examines residual contamination at a former uranium leaching site.
That's a sobering reminder that mining can have long-lasting environmental impacts.
This study focuses on contaminated quaternary sediments that were located beneath the leaching heap. And get this, these sediments were later relocated to a nearby open pit and covered with soil.
So the contamination wasn't just contained, it was moved.
Exactly. And the researchers went in to analyze the extent of the contamination. They measured the pH of the soil and used sieves to separate the sediment into different particle sizes. And what they found was pretty concerning. Elevated levels of all sorts of contaminants, including uranium, arsenic, molybdenum, vanadium, sulfur, iron, manganese, aluminum, silicon, calcium, and magnesium.
And they didn't just stop at identifying the contaminants, they compared the levels to those set by the German Federal Soil Protection Ordinance, the BBUG-FE. Several values, especially in the finer sediment fractions, exceeded those guidelines. This really underscores the persistence of contamination and the need for long-term monitoring and remediation efforts, even after a mining operation is shut down.
It's a reminder that we have to be responsible stewards of the environment.
Absolutely. Our actions today have consequences that can last for generations.
Okay, let's shift gears again and talk about something a bit more dynamic. How fluids move within these heaps. We've got a paper here on the hydrodynamic behavior of heap leach piles.
This is all about understanding how the leaching solution flows through the heap, which is crucial for efficient metal extraction.
So we're not just pouring chemicals on a static pile of rocks. There's a whole flow system going on inside.
You got it. This paper used tracer tests and a mixed flow model to study these flow patterns.
Tracer tests, how do those work?
Imagine interlacing a non-reactive substance into the leaching solution and then tracking it as it moves through the heap. This lets you map the flow pathways and identify different flow zones like plug flow, well-mixed volumes, and stagnant or dead zones. They also looked at how much of the solution bypasses the main leaching zones.
So they're basically dissecting the flow dynamics within the heap.
Exactly. And they did these tests at different scales. Small columns, intermediate-sized cribs, and full-scale heaps, all using the same gold ore from Nevada. They also varied the way the ore was prepared, agglomerated, crushed, and run-of-mine.
Okay, so they're really testing the impact of scale and ore preparation on flow behavior.
And they used the Levenspiel model to analyze the data and determine the relative sizes of those different flow zones. They found that the bulk density of the ore actually increased as the scale got larger.
That's interesting. So the bigger the heap, the denser the packing.
It seems that way. And the well-mixed volume was largest in the intermediate scale crib. They think this is because the crib provided the best balance between solution distribution and mixing, unlike the smaller column and the much larger, more variable heap.
So there's a sweet spot in terms of scale.
Possibly. They also found that a significant stagnant volume only showed up in the full-scale heap, likely due to the higher proportion of fine particles in those larger heaps.
Those pesky fines again. Seems like they're always causing trouble. What about their observations during the actual leaching and rinsing phases?
They found that the reagent concentration was pretty consistent across the top of the heap, but slightly higher on the sides, probably due to evaporation.
So the edges of the heap are getting more concentrated. And during rinsing, they saw a rapid drop in reagent concentration in the outflow. But a significant amount remained trapped inside the heap.
That's right, consistent with that substantial stagnant volume. They even detected tracer solution diffusing sideways from the top, indicating some lateral movement beyond just the vertical flow.
So it's not just a simple top-to-bottom flow. There's some mixing going on. And what about the effect of ore properties on flow and gold recovery?
This is where it gets fascinating. The cribs with non-agglomerated ore, both run-of-mine and crushed, had terrible gold recovery. They were densely packed, had almost no airspace, and a whopping 88% stagnant volume.
88%? That's crazy. So
Yeah.
most of the ore wasn't even in contact with the leaching solution.
Exactly. And what little gold they recovered came mostly from the top third of the crib. but with the agglomerated ore.
Ah, the agglomeration makes a
A
difference.
huge difference. They got much better gold extraction, 86%, because the agglomerated ore allowed for better solution and airflow, a fully well-mixed solution, 10% airspace, and no dead zones.
Agglomeration is like creating highways for the solution to travel through the heap.
You got it.
Okay, so we've covered gold, uranium, and the importance of flow. Now let's move on to another key metal, copper. We've got a paper here that looks at copper leaching from the Dizelle deposit.
This study focused on how particle size and acid concentration affect copper recovery. And one of the key findings was that grinding the ore finer had a bigger impact on recovery than increasing the acid concentration beyond a certain point.
So it's not just about throwing more acid at the problem. The physical preparation of the ore matters too.
Absolutely. They also found that higher acid concentrations led to more iron dissolving into the solution, which can complicate downstream processing, and that finer particles and higher acid concentrations meant more water loss.
So there are trade-offs to consider.
Always. And the paper also provides a detailed characterization of the raw ore from the Dizelle deposit. High silica content, copper mainly present as malachite and atacamite.
And iron as goethite. They didn't find much chrysocolla or clay, though, which is good news because those can sometimes be problematic in acid leaching.
Exactly. They even did microscopic analysis to confirm the presence of copper and cobalt within the ore particles.
Wow, that's getting down to the nitty-gritty. And their leaching experiments really emphasize the importance of particle size.
Big time. With a relatively high acid concentration, they saw a huge drop in copper recovery as particle size increased. But even with very fine ore, a low acid concentration just didn't cut it, so there's a balance to be struck.
You need enough acid to drive the reaction, but grinding finer can be more effective than just using more acid. They also figured out a way to remove iron impurities from the pregnant leach solution by precipitating it out as lepidocrosite.
And they did this without losing any copper. It's a win-win.
Now let's switch gears one last time and talk about zinc. We have a paper here on leaching a zinc concentrate using hydrogen peroxide.
This study focused on the kinetics of zinc dissolution and explored the use of complexing agents to boost recovery.
Hydrogen peroxide, that's interesting. So not the usual sulfuric acid leaching.
Right, this is a different approach. And they found that the leaching process follows the shrinking core model, even though a layer of sulfur forms around the zinc mineral particles.
You'd think that sulfur layer would slow things down.
You would, but the rate-limiting step turned out to be the chemical reaction at the surface of the zinc particles.
So the reaction itself is the bottleneck, not the diffusion through the sulfur layer.
Exactly. They also found that adding complexing agents like phosphonic acid, phosphoric acid, oxalic acid, and citric acid enhance zinc recovery. These agents probably bind to the zinc ions and prevent them from reacting in ways that hinder further dissolution.
Interesting. It's like giving the zinc ions a chaperone to help them along. And they also looked at the effect of hydrogen peroxide concentration, right?
Yeah, they found that zinc recovery was very sensitive to low peroxide concentrations, but leveled off at higher concentrations.
So there's a point of diminishing returns. More peroxide doesn't always mean better recovery.
Right. And just like with copper, particle size and temperature mattered too. Finer particles and higher temperatures led to better zinc extraction.
Makes sense. More surface area and more energy mean faster reactions.
They even confirmed that the leaching was controlled by the chemical reaction rate using a bunch of different kinetic models and calculated the activation energy for the process. It was a very thorough study.
So they really nailed down the mechanisms behind zinc leaching. And now for something that can actually throw a wrench into the leaching process.
Oh.
Jarosite precipitation. We have a paper here on modeling jarosite precipitation in bioleaching columns.
Ah, yes, jarosite. A tricky little mineral that can really mess things up.
Okay, back up a bit. What is jarosite and why is it a problem?
Jarosite is a mineral containing iron and sulfate. It forms in acidic environments, and it can really slow down bioleaching, especially if chalcopyrite, which is a common copper-bearing mineral.
How does it slow things down?
Well, ferric ions are super important for bioleaching. They help break down the chalcopyrite and release the copper. But when jarosite forms, it essentially sucks those ferric ions out of solution.
So it's like a thief stealing your key ingredient.
Exactly. And this paper built a mathematical model that includes all the key reactions in chalcopyrite bioleaching, including jarosite precipitation.
So they're trying to simulate the whole shebang.
They even incorporated the shrinking core model we talked about earlier, and a really important factor they considered was the solubility of ferric ions, which changes with pH.
Right. The acidity of the solution affects how much iron can stay dissolved.
Exactly. And they found that they had to use very small steps in their simulations because jar site precipitation can cause abrupt changes in the system.
So it's like modeling a system with sudden jolts.
And the results showed that jar site precipitation starts in the lower sections of the column and directly reduces the chalcopyrite leaching rate in those areas.
So it's not just a theoretical concern, it has a measurable impact on copper extraction. And they also tested the impact of different inlet pH values, right?
Yeah, a higher inlet pH shifted the jar site precipitation zone higher up in the column and slightly decreased the overall copper extraction. They even explored the effect of changing the dissolution rate of the gangue minerals, which also altered the pH and precipitation patterns.
It's like tweaking different knobs on a complex machine, see how it responds.
Exactly. This study really highlights the interconnectedness of all these processes and how seemingly minor details can have a big impact on the overall outcome. And finally, let's talk about acid mine drainage, or AMD, and how fly ash can be used to neutralize it.
AMD is a nasty environmental problem. It's basically highly acidic water, often laced with heavy metals, that can leach out from mines and pollute the surrounding environment.
It can be a real mess. And this paper explores a passive treatment approach using fly ash, a byproduct from coal-fired power plants, and the residues from treating AMD with fly ash.
Passive treatment, as opposed to an active treatment system that requires pumps and chemicals and constant monitoring.
Precisely. The idea is to create a reactive barrier using these solid residues. They actually did column experiments where they mixed these residues with varying amounts of fresh fly ash and even some ordinary Portland cement to test their neutralization capacity over time.
So they're testing different recipes to see what works best.
Exactly. They found that all the mixtures went through different buffering stages. Initially, the pH was very high due to the calcium oxide in the fly ash and the hydration reactions in the cement-containing samples.
So it starts out very alkaline.
Yes, and then they saw sustained buffering in a more neutral pH range, between 7 and 9.5 for the residues and fly ash-only mixtures. This was probably due to the slow dissolution of silica and mullite.
But the cement-containing samples didn't show that sustained buffering in the neutral range? What happened there?
Well, they think the cement created a physical barrier around the reactive particles, slowing down the interaction with the AMD. It's like encasing the fly ash particles in a protective shell.
So the cement, while helpful initially, actually hinders the long-term neutralization process. That's counterintuitive.
It is. They also did detailed mineralogical analysis to see how the solid materials change after reacting with the AMD, and they tracked the alkalinity and gypsum saturation of the outflowing water.
And they found that strange alkalinity pattern in the samples with a small amount of cement, an initial spike, followed by a drop.
That was due to the formation of portlandite from the cement hydration, followed by its reaction with sulfate to form ettringite.
So a cascade of reactions is happening.
It's a complex chemical dance. They also concluded that the lack of sustained buffering in the cement blends was due to that physical encapsulation by calcium silicate hydrate gels, like the cement created a diffusion barrier.
So the AMD had trouble reaching the reactive fly ash particles, and they also mentioned the role of iron and aluminum compounds in buffering at lower pH levels.
Yes, ferric and ferrous sulfates act as buffers in very acidic conditions. And their simulations suggest that jar site precipitation was likely happening in the pH range of 6.5 to 7, but it would dissolve again at a lower pH.
Ah, Jarset again. Seems like it pops up everywhere.
It's a ubiquitous mineral in these systems. They also found that aluminum hydroxide precipitation controlled the aluminum concentration over a wide pH range.
So the system is constantly adjusting, with different minerals precipitating and dissolving as the pH changes.
It's a dynamic equilibrium. The key takeaway here is that these precipitated phases remain stable as long as the pH stays in a neutral to slightly alkaline range. But once the buffering capacity is exhausted and the pH drops.
Then those contaminants can be released back into the environment.
Exactly. It's a delicate balance.
Okay, let's shift gears one more time. I know we have one final paper to discuss, and it's all about using polymers to improve copper leaching.
Oh, yes. This paper focuses on a common challenge in heap leaching fines migration.
Fines migration. What is that exactly?
It's when those tiny ore particles, the fines, move around within the heap and clog up the flow channels. This can lead to inefficient leaching and lower metal recovery.
Ah, so those pesky fines strike again. They really are troublemakers.
They sure are. And one way to combat fines migration is through agglomeration.
Agglomeration. Is that like clumping the fine particles together?
Exactly. You bind them to the coarser particles to create larger, more stable aggregates. This helps to maintain permeability and prevent those fines from clogging everything up.
It's like creating bigger chunks that the leaching solution can flow through more easily. But there are challenges with current agglomeration methods, right?
The main problem is that the bonds formed using the typical raffinate solution, which is basically the leftover leach solution, are fairly weak. Those agglomerates tend to break down under the acidic conditions in the heap.
So they don't hold up very well.
Right. That's where binders come in. These are additives that can create stronger, more acid-resistant bonds between the particles.
They're like the glue that holds the agglomerates together.
Precisely. And this paper delves into the different types of forces that can create those bonds. There are molecular forces like van der Waals forces, valence forces, and non-valence forces, including hydrogen bonding.
And electrostatic forces, magnetic forces, and even forces related to adhesion, cohesion, capillary pressure.
The list goes on, but they focus on hydrogen bonding as a particularly important mechanism.
Why hydrogen bonding?
Because hydrogen bonds are relatively strong compared to some of those other forces, and they're also very common in these systems. For example, they can form between the binder molecules and the surfaces of silica minerals in the ore.
So it's like a chemical handshake between the binder and the ore particles.
Exactly. And the paper describes a soak test they use to evaluate different binders by measuring fines migration.
So they basically dunk the agglomerates in a solution and see how much of the fines wash away.
Pretty much. They found that binders with a positive or neutral charge, cationic and non-ionic, performed much better than negatively charged binders anionic. They think this is because of the increased potential for hydrogen bonding with those cationic and non-ionic binders.
Interesting. So the charge at the binder affects how well it sticks to the ore.
Yes, but to really nail down the importance of hydrogen bonding, they did soak tests with pyrrhotite, an iron sulfide mineral that doesn't have the same hydrogen bonding sites as silica.
And what did they find?
The polyacrylamide binders were much less effective at reducing fines migration with the pyrrhotite. This strongly suggests that hydrogen bonding is indeed a key mechanism for these binders.
So it's not just about charge. The specific chemical interactions matter too.
Absolutely. And they also point out that some of these polyacrylamide binders are considered safe for the environment, but it's crucial to follow all regulations. You don't want to solve one environmental problem by creating another one.
Right. It's all about a holistic approach. Now, I know we have one last paper to discuss, and this one dives into some pretty heavy-duty thermodynamics.
This is a big one. It delves into a framework called thermodynamically constrained averaging theory, or TCAT, for modeling flow and transport in porous media.
Okay, I'm already feeling a bit overwhelmed. Can you break that down for us?
It's basically a very rigorous way to model how fluids move through porous materials, like, a heap leach pile.
Okay, so it's still relevant to our topic.
Very much so.
Yeah.
It's about building a solid theoretical foundation for understanding these complex flow processes.
And what makes this TCAT approach special?
Well, it starts with a fundamental principle, the second law of thermodynamics, which deals with entropy and the direction of spontaneous change.
Okay, that sounds familiar from physics class.
They use this principle to derive a general mathematical form for a two-phase flow model. Think of it like a master equation that describes how two different fluids, like the leaching solution and the air trapped in the heap, move together through the ore particles.
Two-phase flow. So it's not just about the liquid. We have to consider the air.
Yeah, exactly. And from this general model, they can develop a hierarchy of simpler models by making certain assumptions and neglecting less important factors.
So it's like a choose-your-own-adventure for modeling flow. You can pick the level of complexity that's right for your problem.
You got it. And the cool thing is that all these models use very precisely defined variables that are directly connected to what's happening at the microscopic level. This gives you a lot of confidence in the results because you know exactly what the model is representing.
So it's not just a black box. You have a clear understanding of the underlying physics.
Right, and the paper goes into a lot of mathematical detail, which we won't delve into here, but they essentially derive three different closed model formulations. The most general one includes all the bells and whistles, considering things like interfaces between the fluids and the common curve where those interfaces meet. Then they have a simpler model that neglects the common curve, and a very simplified model that neglects both the common curve and the interfaces.
So they're stripping away layers of complexity to get to the core essentials.
Exactly. The simplest model actually resembles some of the traditional flow models that have been used for a long time. But by going through this rigorous T-stat derivation, they've essentially shown what assumptions those traditional models are making, which gives you a much better understanding of their limitations.
So TCAP provides a framework for understanding both the strengths and weaknesses of existing models.
Precisely. And it paves the way for developing more realistic and accurate models in the future. Of course, the more complex the model, the more difficult it is to actually solve.
It's a trade-off between accuracy and computational feasibility.
Always. And they also point out some limitations of the TSAT approach. For example, it assumes a clear separation of length scales between the microscopic features of the porous material and the macroscopic flow patterns, which isn't always the case in real-world systems.
So it's a powerful tool, but it has its limits.
Every tool does. But the key takeaway here is that TCAP provides a rigorous and comprehensive way to model flow in porous media, and it can be applied to a wide range of systems, including heap leach piles.
Wow. We've covered a lot of ground today. From modeling leaching processes to drainage systems, green chemistry, residual contamination, hydrodynamic behavior, copper and zinc leaching, and even some mind-bending thermodynamics.
It's been a whirlwind tour of heap leaching science.
It really has. And one of the things that really struck me is that sometimes the most effective way to improve metal recovery isn't just about using stronger chemicals.
Right.
Sometimes it's about optimizing those physical parameters like particle size or making sure the leaching solution is flowing efficiently through the heap.
Absolutely.
And then there's the whole issue of environmental impact. The quest for greener leaching methods is really exciting, and I'm curious to see what innovations emerge in the coming years.
Me too. There's a lot of potential there.
And the idea that we can use byproducts like fly ash to passively remediate acid mine drainage is really promising.
It's a great example of turning a waste product into a valuable resource.
Now here's a final thought for our listeners. We've seen how complex these heap leaching systems can be, with a lot of interconnected factors at play. What do you think are the biggest challenges facing the industry today, and what are some potential solutions on the horizon?
That's a great question.
Let us know your thoughts in the comments below. And if you're interested in learning more about any of the topics we covered today, be sure to check out the research papers themselves. We've linked to them in the show notes. Thanks for joining us on this deep dive. We'll see you next time.
Until next time.